Engineering 303, week 10, Thursday. The agenda we have today is shearing stress for composite materials. And then after that, we're going to start on a new topic, a new subtopic, not a new topic, a new subtopic, which is shearing stress for thin wall. And as I mentioned to you, shearing stress is one of the most difficult topic in this course. Okay. Now, on week 8, I'd like to go back to this problem. Okay, there's a part that I've not done yet. I'm going to copy this first. Okay, so this is continue with example from week 8. Okay, so we have done part A, but we have not started on part B yet. Okay, so let me get everything over first. Okay, let's recall this problem. Okay, so we are tasked to look for P such that the maximum stress is not to exceed 130 megapascal. Okay, so from there we found our we were doing the analysis, and we want to find where has the highest Q/T, right? Then from there we discovered that the highest Q/T ratio is at point B. So point B is at this point over here. Okay, and then from there we found our with our Q/T at point B, we found our Vmax. Okay, so we found our Vmax, which is 260.536 times 10 to the power 3. Okay, so that's where what we did the last time. Did we carry on anymore? Okay, so that's what we did the last time. Okay, so we've not actually finished the problem yet. I'm going to, we have not found P yet. Okay, so I'm going to continue today. We are going to, so we found that Vmax, that Vmax is equal to 260.536 times 10 to the power 3 Newton. And we also aware of the dimensions that we have that is on the previous page, 590, 550. Okay, so we know our distance over here is 590, and then we want to find, we have our 550. So we are going to determine the value of P, right? So with this, we are going to perform static analysis. So what I'm going to do is we're going to do summation of moment Z point A, which is equal to 0. So there'll be 0.5, so minus 0.59 multiplied by P, plus by 0.59, plus by 0.55, and then we have our By. Okay, so if we were to sketch our free body diagram, we know that we have a AY over here, And we know that we have a by over here. Okay. So with this we can find what is our by. So by will be equal to 0.59 p divided by 0.59 plus by 0.55. So this will be equal to 0.59 55.59. So it's equal to 0.518 p. And then from here, we do summation of forces in the y direction is equal to 0. You have ay minus p plus by 0.518 p. So ay is equal to 0.48 p. So now if we were to get our shear force diagram, right? So now if we were to sketch our shear force diagram, so we know this again, this is just a sketch. So this is 0, 0.59, and then you have 1.14. Okay, let me add up. Yeah, 1.14. And then this is our V. So we have 0.482 P. Okay, so 0.482 P. Then it comes down over here, and then it runs horizontal here. So this is equal to 0.518 P. Okay. So we know that 0.518 P is greater than 0.482. So therefore, 0.518 P will be equal to our B max of equal to 260.536 times 10 to the power 3. So therefore, P will be equal to 260.536 divided by 0.518. So we discover that P will be equal to 502.965 times 10 to the power 3 Newton. Okay, that's our P value. Now the second part, okay, we will now look at the second part. I'll paste the question. Now the second part is it's not it's not tricky, but it's a so-called optimization question. Okay. So part B reads the wall thickness of the beam such that the maximum shearing stress at the centroid and the region with the smallest wall thickness are equal. Okay, so we have to ensure now, right? The maximum shear stress at the centroid and the region with the smallest wall thickness are equal. The outer perimeter of the cross section of the beam must remain constant. Okay, so we have to find the new wall thickness of the beam. Okay, so this question very specifically states that the outer perimeter means this outer perimeter cannot change. Okay? This outer perimeter cannot change, right? And it states, okay, wall thickness, right? It states the wall thickness. So outer perimeter. So the outer perimeter of the cross section of beam must remain constant. So you're not allowed to adjust the outer perimeter. So we can adjust the wall thickness, but what is the wall thickness? Okay. So if we were to design the shear flow, that looks like this, right? right? This is the shear flow, right? So one of the rules states that the what? The thickness is perpendicular to the direction of the shear flow. So the wall thickness is this thickness over here. Okay, this is the thickness. Some students during those days, this is a term test that I gave in 2002 winter. Okay, and some student asked me, Eugene, can this be the wall thickness? Okay, let me use a different color. Okay, some students ask me, oh, Eugene, can this be a wall thickness? And the answer is no. Why? Because the shear flow or the wall thickness for non-thin wall analysis, okay, the shear flow or the thickness is perpendicular to the shear flow. Okay, so that's where. So the only wall thickness over here is this is the only wall thickness that can be changed. Okay, not the one in green. Okay, so not this one. Okay, this one is not wall thickness. Okay, the wall thickness is perpendicular to the shear flow Q. Okay. So what remains over here now is we have over here. So I'm going to label 2 points, right? So I'm going to label over here. This point over here is alpha. And over here, this is beta. Okay. So what I'm trying to state at this, the shear flow or the shear stress, okay, at alpha must be equal to the shear stress at where? At beta. They must be the same. So now we are going to write out the formula now. Okay, so I'm going to, based on this view, this is our Z and this is our Y. Okay, so from here, we are going to specify Vy over Izz, Qz alpha, okay, Qz for alpha, divided by the thickness, okay, which we don't know. Okay, so over here, this is our thickness. We don't know. Okay, and then this will be equal to Vy over Izz, and then Qz up to point beta divided by, now this one we know the thickness. Okay, so the thickness is equal to 0.05 because it's 30 millimeters plus 10 plus 10, it gives us 50. So we know what value it is, or yeah, we know the value, the thickness, which is equal to 0.05. Okay, so remember we have a set of rules, right? Regardless of the point of interest, V and I are constant. I repeat again, regardless the location of interest, right? V and I are constant. So we can now cancel out this because you will start to worry, oh, I don't have the thickness, I need to find Izz. Okay, not necessarily true. Because at point alpha and at point beta, right, the V and the I are constant. So we don't need to worry about the second moment of area. Okay. So that is what I'd like to drive to your understanding the fundamental concept is so important, okay? Or the rules, okay? So we now know that we have to now have QZ alpha